hello, good morning to everybody. You see the microphone is active, so let us move to our notability and talking about today another lecture on conservative and irrotational fields. Okay, the word irrotational is new. I will try another way of writing, at least partly, to be clearer. So let me know whether it is better than before or it is worse. So let's start with what we saw yesterday. So a conservative, this is new method, field F, and then the three features. So the first, a conservative field has a line integral that depends on the initial and the final points. So not on the particular path used to connect the 2 points, the 2 extremes. So perhaps it is too small. Let me try to do it. The second, okay, or even larger. We can do even larger. The second is has circulation always equal to 0. So remember that circulation is the line integral on a circuit, so on a path whose initial point equals the final point. Third point is a gradient field. So there exists a potential. So these 3 facts can be all put together by recalling what is being a gradient field. So F is equal to the gradient of U, and so the integral, the line integral of a field F is equal to U of B minus U of A, where A and B are the initial and the final point respectively. Because once you really grasp this point, then you immediately have everything else. First, it is clear that the line integral depends on the initial and the final points only, because here you have U of B, final point, and U of A, and no reference on the particular shape of gamma. Second, as circulation always equal to 0. Why? Because in particular, if you are to compute a circulation, then you have that F dot dr, and gamma is a closed path. You have U of A, which is the final point that coincides with initial point equal to 0. So from this formula, let me call it formula asterisk, you have 1 and you also have 2. And third, it is clear that in the asterisk you have that F is a gradient field. So once you grasp this point, everything is made. But this point can be quite delicate. Today we start a discussion that will lead us towards the fact that there is some touchy points to be really understood. So today I will move to another topic, which is called the topic of irrotational fields. So let me understand whether it is possible to change color, but I don't think so. Yes, it must be possible to change color. Why? Why not? No, it's not here. Okay, sooner or later I will discover how to change color. However, so go to the center and write down irrotational field as a title. Here. It is very difficult for me, sorry, I need some time, so let me move to and there is also the corrector, which is very dangerous, irrotational fields. Good. Non-irritation. Okay, this lecture is irrotational fields. Irrotational. Okay. So this is a first observation, a first remark is the following. Consider a conservative field so it is a gradient field, so that f is equal to gradient of u. And in particular, this means that if I write down f, I don't want to forget the arrows, they are not essential, but they clarify that we are talking about vectors. So if we write down f as component by component, so like f1, f2, f3. So then we have that f1 is the derivative with respect to x of u. I use this short notation dx instead of d over dx. And the second is the derivative with respect of y of u. And the third, the derivative with respect of z of u. Okay? So now, consider, for instance, the derivative with respect to the variable y of f1, so the x component. Okay? Here, we want just to differentiate a component of the field with another variable. So this is morally the x variable of the field we differentiate not respect to x, but respect to y. So this is equal to dy of dxu. But you know from differential calculus for many variable, multivariable function, this is dx of dyu by Schwarz theorem. It was, Schwarz with T. There are two Schwarz, one with T and the other without. This was the one without, it was the German guy, Schwarz, Hermann Schwarz. The other was the French one, Laurent Schwarz, okay, in two different centuries. However, this is the Schwarz theorem for mixed derivative. And then what you find at the end is that this dy f1 is equal to dx and what? So this is f2. So here you have dx f2. So immediately you have that these cross derivatives are the same. And of course you can also compute other derivatives, and analogously you have that dz f1 is equal to dx f3. Okay, there is always an exchange of variables. Here we have the two variables z and x, because f1 is the x component of f. And here again you have z, because f3 is the z component, dx. So you have to exchange them. And then you have the z f2 is equal to dy f3. And so you have these three rules, okay? And remember that at the beginning we introduced what is called the curl. So the curl of a vector field. The curl, I write it here better, curl. The curl is what we call the vector operator that can be written by using nabla, but this time instead of doing the ordinary product or the dot product, we do the cross product. Nabla cross f is equal to the determinant, which is just a formal determinant, e, j, k, and then the component of nabla, dx, dy, dz, and here f1, f2, f3. And now write down the component explicitly, and so for the I component you have dy f3 minus dz f2 plus j. Now remember that there is a minus sign here morally, so here you have dz f1 minus dx f3 plus k and here you have dx f2 minus dy f1. Okay, this is the so-called curl, sometimes also rotational, of a vector field. Now we suppose, in addition, that f is conservative then look at the previous equalities. For instance, you have here dy f3 minus dz f2, but here we have that dz f2 is exactly equal to dy f3, so this is equal to 0. The I component is equal to 0. And for what concerns the j component, here we have dz f1 minus dx f3, but here you have dz f1 is equal to dx f3. So also the j component is 0 too. And at the end we have the k component, and in the k component you have here dxf2 minus dyf1. So we use this color here. And this is exactly the first computation that we made. So if f is conservative, then we have that the curl of f, which means nabla cross f, is equal to 0. Let me give here a definition. A field whose curl is 0 is called irrotational. And then here we have first a theorem, but it is a small theorem. Let me call it proposition. Proposition says, sorry, I don't want this. Conservative field is always irrotational. And so this gives us a criterion of non-conservativity, and as a consequence, one has that an irrotational field, that if the curl of a field f is not 0, and I mean identically 0, so 0 in all points, then f is not conservative. So it's a sort of negative criterion. We are still not able to say if a field is irrotational, then it is conservative. We are not able, it will not be really true, we will see. But on the contrary, we are sure that if a field is not irrotational, then it is not conservative. So if I take an old exercise, if I'm able to find it quite rapidly. So the exercise was the one with a helix. So we have. Let me write. So without the arrow, then I will put the arrow too. So we have f x y z was equal to what? To 1 cos t, if I remember well. Up. Sorry, I'm looking for this field, this exercise I gave you. And so if I remember well, this was, no, it was 1x or 1 was z Okay, it was 1x, and you remember that we integrated in two paths and we did not find the same result. Of course, I made some mistake on that, but still, I don't want to correct now this mistake. I just want to answer to this question: is this field conservative? So the answer that we now can give is to try to build up potential. But first, it is very easy to verify. So let's do it first. Verify whether this field is irrotational. And so we have that the curl of F is equal to what? Okay, here I have to use the pen. So the first component, I recall you, is dyf3 minus dzf2 then dzf1 minus dxf3, and the last component is the x f2 minus dy f1. So let us use this this field. Let us use this formula, and we have that okay, all the derivative with fx or fy are 0 because the two fields here are constant. So where you have f1 or f2, for instance here, here, here and here, you always have 0. Then look at f3. f3 is equal to x. So if you differentiate it with respect to y, then you find 0. What remains here is minus dxf3, and this is equal to minus 1. So the curl of f is 0, minus 1, 0. And so I recall you what we did in the exercise. So in the exercise we computed the line integral. So in a previous lecture we computed the line integral of f along two paths. One was a helix, whose equation was r of t equal to cosine of t sine of t 1, t, for t in the interval 0 to pi. So r dot of t was minus sine of t cosine of t 1, and the f of t along the curve r of t was 1 cosine of t. So it turned out that the integral of gamma of f dot dr was the integral between 0 and 2 pi of here there was minus sine of t So here we have to, here you have minus sine of t plus 2 cosine of t in dt. And so the final result was 0 because all these periodic functions has average equal to 0. And the second attempt was on the other path, was the segment joining the initial and the final point. The first point was 1, 0, 0, and the last point was 1, 0, 1. So, sorry, 1, 0, 2 pi, not 1, 0, 1, 2 pi. This is pi. Okay? So the integral, so r of t was 1, 0 t with t in 0 to pi. R dot of t is equal to 0, 0, 1. Again for t in 0 to pi, and f of t was 1 x originally, so 1 x. So here we have 1 1 1. Therefore the integral on this new gamma, that was called gamma 2, is equal to the integral from 0 and 2 pi of 1 dot 0 0 1 dt. So this is equal to 2 pi because it is just the integral of 1. And so I mistook this part when doing the exercise the last time. Thank you to the one of you who told me that there was a mistake, and I think that this time things go better. Thank you very much, but I want to stress the important fact, and this was true also notwithstanding my mistake in the previous lecture, but the important fact is that the two results are different. So we have here two paths joining the same couple of points, but the line integral of the vector field along these two paths give two different results. So it is not conservative. It is not irrational, so it is not conservative. So this is the first part, and now we go further. Thank you.